Good morning. Can everybody hear me? Okay, thank you. I haven't run a marathon, so I don't know what it feels like, Jim. Maybe one of these days I'll do that. So my name is Debendra Das Shama. I work for Intel, and I lead the IO technologies and standards group there. Part of the other hat that I wear is I am the chair of the Phi Logical work group in PCI SIG. So I'm here on behalf of the PCI SIG, which is an industrial consortium, as you all may know, to talk about how PCI Express has been evolving, and most importantly, to get your feedback in terms of what kind of new usages, new technologies you would like to see coming in this, coming into this interconnect technology, right? So with that, the agenda-wise introduction, then I'll talk about a little bit about 4.0. I won't go through it in a lot of details because the materials have not been released, so I'll just give you a little bit of a preview there. I'll talk about retimers. Those are becoming very important, especially as we go towards Gen 4, more than 8 gig kind of data rates. Talk about form factors, talk about a little bit about how the SIG does its compliance program, and then conclusions. So, looking back, right, PCI started off as a multi-drop bus kind of an interconnect way back in 1992, okay. So, the first incarnation was 32-bit, 33 megahertz, you went through 64-bit, 66 megahertz, 132 megahertz, the evolution continued till we realized that the bus-based multi-drop kind of interconnect is really running out of steam, and it is not the best way to hang off your I/O, right? You always have some citizens on the bus that are slow and some that really want to get more bandwidth, right? So, naturally you want to move to something that is a little bit more modern, and hence we move to the link-based serial interconnect technology with full duplex signaling, right, with PCI Express. This was around the time when InfiniBand was also coming out, okay? So about coincident, give or take some. But what's more important from a PCI SIG and the technology, PCI technology point of view was we maintained full backwards compatibility from a software point of view. Not from a hardware point of view. You cannot take a PCI bus-based device and hook it into a PCI Express links-based device. But from a software point of view, it looked identical. Yes, there were few extensions on PCI Express. If you didn't have the latest software, you didn't take full advantage of it. But from a plug and play model point of view, it worked, okay? So that's basically what is the promise of this technology, is that we try to even make things work from a pin-to-pin point of view within each, even within each of these major transitions that we do, like bus to links. But within each of those, we try to make it pin for pin compatible, but at least when we do the transition, we want to make sure that you don't have to rewrite your entire software stack. It will work the way it used to. Within PCI Express, and I'll show a picture in the next slide, we have been doubling the data rate every single generation, and you'll see the cadence in which we are doing that. And 1992, it was all about the PCs, right? You want to interconnect your printer, you want to interconnect your disk drive, what have you, right? And your Ethernet card, all PCI based. So from PCs to, it has evolved to the HPC segment, the servers, the clients, the handheld, Internet of Things, everything over the last few decades. And it has not happened because it is a static technology. As you will see, we have been constantly innovating on this technology to make sure that we are comprehending the needs across this diverse segment of compute interconnects, compute technologies that we are facing with, right? So this is a cartoon picture, right, of what a PCI based system looks like on the left. So what you have is, you had a processor, you had a host bridge that connected to memory, you had some graphics, you had a PCI bridge, and then, out comes a few PCI, it was not uncommon to have a few sets of PCI bridges, and then you got a bunch of PCI devices connected there. Move into the next decade, right, 2000s, and now into 2010s, right? This is what the world looks like. And you will see in the next slide, so we used to have a CPU, we used to have like a root complex, and today these are all integrated into one processor, right? That's Moore's law. playing out, right? More and more integration happening, less and less components in the system. And as a result, we are able to deliver better performance with a lot lower latency, and that will come up in the next. But fundamentally, Express it's a point-to-point, right? So you want to hook storage, hooks directly. You want to hook network, hooks directly. You want to get more expansion, there is a PCI Express switch, but from the switch, again, everyone is sitting on its own PCI Express link, right? There is no bus sharing. In the SoC world, you got your CPUs, you got your SoC interconnect and root complex, and then a lot of PCI Express integrated endpoint, right? People are integrating networking within the same die, but fundamentally the architecture from a software point of view, it's a PCI architecture, right? The same discovery model works, same everything works. So this is a little bit of what I was saying, right? A pictorial view. So PCI Express started off somewhere over here, right? In 2003, 2004 kind of time frame. This was Gen 1. So we started around 2.5 gigabit transfers per second data rate. And this is when actually products came out. The spec was available, shortly before that, but this is when actually products were available in the market, right? And this is the gigabytes per second, right? In terms of a by 16 number. But you'll see that, so we come here, then in 2007 roughly, you start seeing server products doing PCI Express Gen 2 at 5 gig. Okay. 2011, we are at 8 gig. So again, 5 to 8, it's not quite doubling the data rate, but we made a change in the encoding. So 8-bit, 10-bit, we lost 25% of the bandwidth in the process. So we captured that back, and I'll talk a little bit about that encoding mechanism. So the net result was we gained about 2x bandwidth improvement on a per pin basis. So from there to there. And then coming forward, we are at 16 gig. Okay. So you'll see that the innovation cadence continues. And if you look into in the meanwhile, how has a typical system looked like, right? And these are some of the systems that I have worked on. So these are our Intel-based kind of systems. So and other systems would look very similar. Okay, there's nothing magic about this. You got a few sets of CPUs sitting on a front-side bus kind of an interconnect. Then you got your memory and I/O controller from which memory hangs off there, and then you got PCI Express links coming out. So that was the mode in which things were working in this time frame. Fast forward to this time frame in 2007 onwards. By this time, you will see that memory gets integrated into the CPU. Okay, and I don't want you to be hung up on the numbers, whether 2007, 2006. These are rough kind of time frame numbers. Okay, so memory gets integrated into the CPU. Again, Moore's law in work, right? More and more real estate is available on the die to do more and more integration, but I/O still sits on this is a coherent link, right? I/O still sits on an I/O hub, and this, by the way, is the Tylersburg Boxborough chipset. That's the picture I'm showing, and there was a hot chips paper. So each and every one of this has a external reference that you can go and look up. Okay, so it gets integrated. You have PCI Express 2.0 lanes coming out. And look at the number of lane counts, right? You will see that the lane counts is increasing. Not just the frequency is increasing, the lane count that is offered on a per socket basis is increasing significantly. Come forward in around 2011, now the I/O hub is gone, everything gets pulled into the CPU. As a result, not only do you get the number of lanes scales with the number of CPUs, but also the number of lanes within its socket is increasing. So if you work through all of these numbers, you will see that even though the changes are happening in a 3-4 year kind of cadence, right? If you plot it into an average annual CAGR of PCI Express performance, it's growing at, on an average, more than 30% per socket, which is again consistent with the performance that you get out of a socket using your favorite benchmark, right, of choice. It is increasing at that kind of a rate, right? So it's keeping up with that. Some of the other things that are happening which are interesting is, start looking here, you get I/O virtualization that's enabling you to do device sharing, right? Much more important in the server kind of usage models where you want, VMMs are becoming popular, more and more VMs people want to load up. So this is what is enabling that to deliver the I/O performance without everything having to go through a VMM and having the VMM or some kind of a I/O container emulating the I/O virtualization in software. That's a lot slower process. We basically made I/O virtualization as part of the standard, right? In this time frame, you will notice that, especially with integration happening, we are providing a lot of caching hints into the CPU, saying, so a device might say, hey, I'm reading this cache line, but keep it around, I'm going to come back to it. I might do a write, or vice versa, right? You can start giving hints so that you can use a huge caching infrastructure to your advantage for doing I/O, right? As opposed to having to go all the way to memory, fetch the data, and you're not only saving on the memory bandwidth consumption and the power consumption, but also you're getting a more effective performance because you are able to access the last level cache or whatever be your choice of the caching hierarchy, right? So, recollect that in the 1 gig kind of time frame, there was a lot of talk about, would we be able to sustain the data rate on a 1 gig Ethernet, right? That was the talk, more than a decade back, right? For those of you that recollect, right? We are going through 10 and all of that very easy, right? And guess why? Because we are effectively able to use the LLC as the place that, the course and then the I/O coordinate, right? So all of these are coming from those. A lot of improved power management features, lower latency, access to the cache gives you lower latency, but improved power management. Atomic operations is because we foresee in this time frame that there is a need for accelerators. And for that, you want to provide some kind of a semaphore semantics, which was not there in the PCI Express. So atomics are basically providing you with that semantics, okay? So you'll see that, a lot of, not just the speeds and feeds increases, but we are basically looking at the ecosystem and trying to see where is the demand going to come from, right? What are the needs, right? What can we do to make this technology useful for the consumers out there, right? And the consumers, as I said, are a very widely varied bunch, everything from a handheld all the way to up to the HPC, right? Improved power management. So let me say a bit about that. Of course, we do have power management features. Everybody has power management features, but and you will see that the power efficiency of PCI Express is fairly good. That's coming up next. We were not doing a good job in terms of our idle power with the existing power management flows that we had in PCI Express. Specifically, when you looked at MIPI, right? Our idle power was in milliwatts, MIPI's was in tens of microwatts. And we had to close that gap, which is what we did. Right? We basically introduced substrates of power. It was just there. It was just that the demand was not there in this segment. So, why bother, right? You have a power socket connected to, whereas if you are working on battery with this, it's a different ballgame, right? You want to preserve every microwatt that's possible, right? And which is what we did there. So PCI Express, it's a layered architecture. So you have different layers here. So depending on whichever way you want to start from, at the very bottom is a mechanical layer, right? So this defines how things hook together, right? Is it a chem form factor? Is it a U.2, which is your 2.5-inch SSD kind of form factor, or before that the disk kind of form factor? So different form factors, or M.2 for the handheld segment kind of form factor. So different segments have different needs in terms of what kind of form factors, and by the way, what type of capabilities they're going to get, right? Each of the form factor comes with a power envelope and all of those kind of things. So that's that. So these are market segment specific form factors, and they evolve, and then there are also revolutionary form factors, right? Electrical and logical PHY, this forms the physical layer. So this is responsible for doing the physical layer exchange, right? What speed should we operate on? What is the, how do we train? How do we understand what channel is it, so that we are operating at the optimal operating condition, so that we get the desired bit error rate. So it's all of those. And this is the data link layer, which is basically establishing a reliable connection between the two sides, right? I mean, standard stuff like you have a CRC, you have link layer retry in case something goes wrong, right? You have some standard link management kind of functionality, right? You have mechanisms of exchanging credits between the two sides. All of those kind of things come in here. transaction layer, so this is the split transaction based protocol, right? So, standard things like, I issued a memory read. I'm not going to go and keep polling on you to give me that memory read back. I issued you a memory read. I expect the completion at some point of time. It's a split transaction protocol, right? It's fully packetized, packet-based protocol, split transaction, credit-based flow control. We have virtual channels so that, you can mix different traffic types. Some might have isochronous needs. Some might have more of a bandwidth guarantee need, right? So you can mix and match all of those in different virtual channels and traffic classes. So that way you can provide the quality of service guarantees for each of those, right? And the spec defines mechanisms for doing that. So that's that, and you'll see that all of these are based with a standard defined configuration register, and this is where we try to establish, when it was PCI to PCI Express, we preserve those config registers. Yes, we added quite a few, but we defined it in such a way that it would still work, even if the underlying software on the top did not change. On the software side, it's all PCI compatibility. There is a configuration mechanism. There is a driver model, right? It's all very standardized, and PCI Express also defined an enhanced configuration model, and what that means is configuration registers used to be 256 byte in PCI, but as we move into this time frame, we expect devices to be getting smarter and able to do more and more things. So 256 bytes is a very limited way to express your capabilities. So we went ahead and defined, kept it compatible, but defined it in a way where you can add to it, right? So that way, you could define a bunch of capabilities, and it's very well defined. It's a linked list kind of structure. So you can define first capability, second capability, third capability, just keep linking them. It just works, right? Software knows how to go and discover those. It's pretty standard, right? So the key thing here is, right, not only do we maintain compatibility between generation to generation, but also you will notice that we do not do, right? And let me repeat this, and I don't want to point out to other parts of the industry that do this, right? We do not do specialized protocols for specialized applications. It's all built within this stack, and we are able to maintain this, right? Best example is NVM Express. Yes, it's a different protocol. It sits on top of this. It's still, everything else still works with the same driver model, with the same, you still have your same producer-consumer ordering model. You still have the same architected models. You build on top of this, right? That's the goal. So I promised that I'll show you the power numbers, right? And we just show the number with MIPI, right? And the power tends to be, as I was telling earlier, that power tends to be the area where MIPI used to do better, and as you will see that we have closed the gap. So very comparable speeds, right? 5.83 and 3.0 is 8. This is this, and these are the active power numbers. And by the way, these numbers comes from a known IP vendor, Synopsys, right? This is not us, Intel. We do not release our power numbers, right? But given that they are an IP vendor, they do publicize their numbers. So look at the numbers, right? Very compelling. And by the way, the standby power number, we have closed the gap. Okay, so a lot of people do not internalize this, right? But PCI Express is lower power, higher performance, lower power. So let me now switch gear and talk a little bit about PCI Express 4.0. Need to pick up my pace a little bit here. 4.0 data rate is 16 gig, right? As I showed earlier, 2.5, 5, 8, with the funny math of 8 being 2x of 5, and then 16, right? Fully backwards compatible with all the other previous generation. We want to keep the cost low because of the segments that we are going across, and that's a huge challenge for us, right? If we could rely on better materials, better connectors, better everything, right, the cost will go up. Then we are no longer going to be able to satisfy that entire continuum of compute that we are going to serve. Higher performance and low power. And connector improvements are there to reduce crosstalk and improve the insertion loss at 8 gig. So that's the change we had to make for going from 8 to 16 gig. And fundamentally, in the Gen 4, so earlier in Gen 1, Gen 2, Gen 3, you could go 20-inch 2 connector easily. But in the time of Gen 4 came along, basically we said, look, this is, you are going to get FR4 type of materials, they're going to have a huge variability, you're going through the motherboard, all of these losses, and the packages are becoming bigger and bigger as the CPUs are, getting more and more capable. It's a difficult proposition, right, to stay without anything in between to go to 16 gig. So we basically have comprehended two types of channel. So this should be, instead of calling it a short channel, you can think of it as a low loss channel, but this will be mostly your desktop kind of channel, right? You can go directly. This is about 12-inch one connector. If you want to use the same old materials, 20-inch two connector, you need to put a retimer in between. But you'll still go there. And the spec defines a retimer spec. The PCI SIG defines a retimer spec. We do what is known as transmitter equalization, right? So given that there is so much of variation in the channel, given that there is so much of variation in people designing their receiver, and every receiver design probably is going to be different, what we came up even at that time of 8 gig is we basically said that a fixed level is not going to work across. It's not, we are way past the one size fits all kind of model. So fundamentally what we said is every receiver, that means on every lane, is responsible for making sure that it trains its transmitter in such a way that it's going to work. And then the spec allows for a handshake on how that happens, right? And there is an analysis that we did here for 8 gig, 18-inch 2 connector channel. And we showed that, even if you magically came up with the best preset, let's say, first of all, everybody will have a different preset. Even if you magically came up with a different preset versus you try to train, and this is taking into account the variations that you are going to see, right? The dynamic kind of the training of your transmitter based on your receiver yields you a better eye. So the spec A allows you to do this if you can work with that, or if you want to go over here and do much more finer tuning, it allows you to do that, okay? So what the transmitter needs to do is, it's the receiver's choice of how it manages it. A transmitter is mandated by the spec to give whatever the receiver asks for, as long as it is within the legal boundary that the spec defines. So this one goes through a lot of the equalization kind of handshake, and basically it's a 4-step kind of process. So you basically try to go and figure out, first step, you start off with a known preset so that the link operates at 10 to the power minus 4 bit error rate. The spec's operating point is 10 to the power minus 12. But the first step, you just start off with a known point which will give you about 10 to the power minus 4, and then each side will train. So first step, the endpoint will train the root complex so that this goes to 10 to the power minus 12. And the next step, root complex will try to train on this link and go to 10 to the power minus 12. So that's basically what happens. So this one goes through a picture of showing the first step, this link is getting trained. So, you start off with a certain preset, and the endpoint requests it moves from here to here. This guy applies that. Then the receiver here evaluates, saying, hey, my link improved, but I could do better. So it makes a different request. So that request comes in, it applies, it says, link got even better, but not quite at 10 to the power minus 12. So it makes a further request, and you can see, right, it's moving from there to there it will eventually move over here. And now the endpoint says, hey, now I'm fine. The link is at 10 to the power minus 12. So it's basically an iterative process, and there is one phase where you are going to go through and do your trial and error, get your link healthy on this direction, and in next time around it will flip. So the same thing will happen in this direction, and now your link is up and running. So that's the process there. So retimers. So the retimers are used to extend the channel reach, and what the retimers really have are this is the full stack, right, that I showed you. But what the retimers really have is this part of the stack. They just have the electrical and the logical PHY. They do not understand, in other words, they just understand the bare minimum that is needed to be able to participate in this link training process. So if it is a retimer, this link is different physically than this link, which is different physically than this link. So this retimer needs to be able to participate in training this part of the link, this part of the link, and this part of the link separately, which is what it is trying to do there, right? And that's what happens. And then the spec defines a way how the retimer will work. So there is a retimer spec built in within the base specification that talks about how, when it needs to, what are the patterns it needs to look for, when does it actively participate in the link training, when it should just step back and pass things through, all of that. NVM Express, right? This is a picture showing, how PCI Express based storage is going to take over, and which is what we see, right? I mean, and why not, right? Look at the number of lanes that are coming out of the CPU. That bandwidth is, as I said earlier, right? It's increasing so far at about a 30% kind of performance CAGR. Coming out of the CPU, the fact that it gets integrated into the CPU means it's the first class citizen, right? And that's where you want your non-volatile memory, whatever next generation you're working on, to be sitting on the in the system, right, directly, because you're offering a very high performance storage, effectively closing the gap with the memory, right? If you look into the distance between DRAM versus where disks were and where NVM is today, it's closing the gap significantly, right? And that's the logical place for it to be. And we are all poised to deliver that, right? So the two main things that are going to drive this technology, and there is a third thing also, are going to be high performance storage, networking, and of course accelerators, right? These are the three main things, right? These are the different form factors, right? The BGA kind of form factor, which is much smaller, and you can think of like the handheld kind of space. This will be important. And even, for example, some people might want to put the retimer on a BGA form factor because you don't want a much more elaborate one, right? You just want to be able to put something on the motherboard directly. M.2, this is again in the handheld kind of segment. U.2, this is where most of the next generation non-volatile memory is headed, and the traditional CHEM form factor, right? So wide range of form factors, and there is a compliance program that goes with most of these. Okay. Other thing that is happening in the form factor space is inexpensive cabling, right? So if you look into the SATA cable, right, PCI Express SATA is moving to a PCI Express kind of PHY, but their cables are much more cheaper cables, right? 50 cents kind of cable, whereas with PCIe cables, if you include a reference clock, the cost goes more than 2x. And this is again very cost sensitive segment, right? But you cannot leave them high and dry, right? So we did make changes in the spec, so that way you don't you increase your SSC from, we used to have -300 to +300 parts per million. We increase that to -50, 300 to +300, so that way you don't need to have some kind of a reference, either a reference clock being sent in a shielded way, and then you can since you have a higher variability of that reference clock, you need a deeper elastic buffer, and you need to send what is known as the skip ordered set, which is used to do the clock adjustment. You need to send that a little bit more frequently. You do end up losing about 2.5% of your bandwidth in the process, but that's fine. That's part of the cost of doing business for going with a lower cable. The spec allows for both. Okay. PCI SIG has a very robust and well-defined compliance mechanism, right? There is a process in which people come with their, let's say, PCI add-in cards. They are going to get a PCI SIG logo saying it meets the logo certification process, right? And if you are an OEM or you are a end user, you would in general insist that the parts that you're using gets logo certified at the very least, right? So it starts with the specs. There is a formal spec in terms of what gets tested that matches with the base specification as well as the form factor specification. So you do that compliance and interoperability test specs. Then there is a test set of hardware and software, and it validates everything for each of the layers that I showed you. So for example, on the electrical side, there is a separate compliance load board, baseboard, which they're going to hook up. They're going to look at the signal coming from the transmitter, try to see that it meets the characteristics. On the receiver side, they're going to stress the receiver, ask the device under test to loop things back so that we see exactly what the receiver is seeing, and do the compliance that way. At the higher level, we are going to inject errors, try to see, are you doing the link layer retry, things of that nature, right? At a very high level, we are going to see, did you define the compliance, the config register space properly? All of those things happens. And then there is a clear pass-fail indicator at the end of it. So you come with your part, go through this process, and then hopefully you get a pass sticker. If it is a fail sticker, you come back again. Okay. So in conclusion, right, we have always strived for, and we will strive to make sure that we have a single PHY that's going to cover all the applications, right, spanning from handheld to server, HPC kind of market, everything in between. Okay, that's why that's the promise of open standard. That's the promise of backwards compatibility, all of that, right? Your investments get protected. It's a predominant I/O, as I said, right? The only ubiquitous I/O coming from the CPU sockets, right? Yes, they do get some other I/Os in some segment and some other I/Os in some other, but across the entire spectrum of compute, this is the I/O that comes out. We are actively developing 16 gig. As I said, a wide variety of form factors, because you cannot have one size fits all, right? The type of form factor for a handheld will be different than a server, for example. But nevertheless, and even within the server, you've got different form factors depending on whether it is a networking card versus 2.5-inch SSD kind of drive. And we have a robust and mature compliance program that ensures interoperability. We are low power, I cannot stress it enough, and of course we are high performance, right? Any questions, comments? And by the way, and if you have any ideas on the type of challenges you are having that you would like to see PCI address, as I said, right, we have been doing things on the transaction protocol layer and things of that to make sure that we remain relevant for the up and coming usage models. I would definitely like to hear about those. Yes.
Yeah, I have a question. Tom Dalpy, Microsoft. Yesterday we had a rather lively discussion about new semantics for PCI Express that would involve support for persistent memory, the commit operation. You didn't really talk about anything above the physical layer, I think. So what innovation can happen above this layer, the protocol, the requests that flow over PCI Express as part of 4.0?
Right. So the question is that as we see the next generation non-volatile memory come across, memory is becoming persistent.
It's already here.
Yeah. Yeah.
Right.
So then the question is what kind of protocol flows can we have in the PCI Express side to make sure that we take advantage of that, right? The reason I didn't talk about that is I'm not here to talk about things that are in progress or things that we are comprehending. What I'm talking about is the things that are already out there. So that's the constraint I have, right? That's my PCI SIG hat here. But I would like to have the discussion with you offline and see what are the usages that we are. We might not be comprehending everything, so I want to make sure that we gather all the requirements. Yeah.
In context of NVM Express, you mentioned server and HPC. Can you enlighten us how the PCI hot plug works today or in future?
Sure. So PCI hot plug works. So there are two types of hot plug going on PCI Express. One,
I mean, compared to the ubiquitous SAS interface.
sure. There are some known like SAS gives you better expandability than what PCI Express does, and so let's talk about the hot plugins in particular, right? Because everything gets mapped into a memory mapped I/O space on PCI Express, hot plug does become a challenge on PCI Express side of the things, right? So for example, if you removed something while it was operating, you are going to get transactions that will time out. And because it is coming directly from the CPU, you are going to get a master abort or target abort depending on how you have set it up. Now there is a, I'm pretty sure this part has been released in terms of the membership, but there is something called EDPC, downstream port containment. Those have been developed to address those kind of issues, right? PCI does support, by the way, hot plug. It works well if
Yes.
it is a if you try to it's a planned hot plug. It does support the surprise
Exactly.
hot plug, but it does have those kind of restrictions where, and this is specifically important in the not just NVMe, but in any storage context, right? Previously, what used to happen was, you got a bunch of SATA drives, and you had a controller that is sitting there. So even if one went away, it basically, it could do, let's say, a raid across all of those SATA drives, and it could hide everything underneath that. Now you're completely exposed, right?
Yes, so SAS is just like our USB, and
Yeah.
I'm trying to see when can we close that gap with PCIe to be like USB and SAS.
Yeah,
to be
we are
truly-
working on that, and I would like to gather your thoughts also. We are working on that, and as I said, take a look into what we have done on the DPC, downstream port containment, and EDPC,
Okay.
and see if that meets the need. If I knew there was interest, I would have put some slides on that also.
Yeah, especially from NVMe and Fabrics
Absolutely,
context now.
yes, we are very aware. The bottom line is we are extremely aware that that's the
Pain point.
That's the pain point.
Okay.
I won't say that we have addressed all of them. Like I said, for example, we know that SAS you can expand. Okay, you can keep expanding. Whereas here we are limited by the bus device function, which is 256. Okay, so we are aware of those kind of things. We are working on those, but there might be things I would like to see if there are things we are missing.
Is it part of 4.0 or it's post 4.0?
I don't want to really comment on things that are in progress. I'm sorry, but the fact that we know about all of this and we are working on it should tell you something, hopefully.
Okay, thanks a lot.
Yeah.